Hello and welcome to this tutorial. I'm going to talk about ASA, some structural analysis. Um, let's run the application. I already installed it. I showed in the previous video how to install it. It's simple. Just click next, and then you're done after downloading the executable file. Okay, so you start from left to right. I'm going to go in a basic, I'm going to do a basic beam example. Here are the elements. Starts at node 1, start at 0, 0, go to 120 inches, which is 10 feet, and it's going to be a beam element, not a truss. I'm not gonna subdivide the element further. I'm gonna leave it as one. You can use custom section by inputting the area and the moment of inertia about the strong axis. I'm gonna show you how to use the American Institute Steel Construction database. You can start by typing. If you have a W shape in mind, you can type W. It's give you the lightest weight possible. As you start typing, it starts filtering. I'm gonna do 1, it's gonna give you 10. Go 8, it's gonna give you W18. And then if you want another section, you can select it from the bunch of whatever W shape you're using. You don't have to type the entire section, but uh, don't type like a section that doesn't exist, because it's not gonna tell you. If I type W88, there's not such a thing. So just go to custom section. Um, so I'm gonna use this section real quick. So I can stretch. You can see these numbers are depopulated for you. Area and moment of inertia about strong axis. Okay, so you can add supports. You can add a pin supports called hinge at node 1. You can add node 2. Add a roller. It has more values because you can place it in kind of an incline. So if you put it at 30 degrees, for example, angle, it's gonna show it's a 30-degree angle. I'm gonna just or make the beam to slide free in the X, and that's the normal one we need to use. So it has this symbol, which means it's kind of not attached to the floor. It's attached but not fixed to the floor, which means it can move. Go to the load. You have three types of loads. You have a nodal load. Let's make an axial load here so we can show the axial. I'm gonna let's just you can place the components of the point load that you have, or let's see if we want it in a 45-degree angle. You can put -10 in the X, -10 in the Y, and it's gonna give you calculate the load for you, and it show you the placement. I'm gonna remove it. I'm gonna just have one in the X axial. I'm gonna just make a small one, maybe -5, smaller. Okay, add it there. That's point load or nodal load. Basically, you have to have a node before you apply this one. If you want at the center, make two elements equal length, and then you'll have a node here. Place a point load there. Okay, so distribute load, you can place triangular or trapezoidal or uniform, and then you have directions in the X, the Y, or the elements. These ones, on this case, they're going to be the same. Elements and Y is going to be the same, but elements is basically always perpendicular to the beam. It doesn't matter if it's in an incline, it's going to be perpendicular. The Y is going to be gravity load pointing downward. In this case, the Y and the element are the same. You can do like a trapezoidal load if you want, or triangular load if you have this one at 0. Um, you just have a uniform distributed load, and you just leave it at elements or Y, it doesn't matter. As you can see, you can change values here if you want on the table, but you can't use things that doesn't exist. Like we have an elements 1, we don't have other elements, so but we have, for point load we have two nodes, so you can be careful about changing these ones, or or these ones. Software doesn't look at these ones, look at the table. So this is just your inputs. You use it to think of it just like a scratch pad. This is your loads. When you apply them, you add the structures. Okay, analysis, render analysis. Let me go back to the load. The moments, if we place a moments at node 1, node 2, it's kind of like the point load. You have to have a node to apply a moment. Okay, so that's done. Let's go to solve structures. Will give you a table. You can save it as a text file or copy the values to plot it on Excel, like the shear, moments, displacement, axial, all that. Or you can view them here. You can see reactions, bending moments. Bending moments basically it's showing you where to place the rebar. This is common in other softwares. They don't show it to you positive. Yeah, that's why, because you need the rebar at the bottom. Wherever the moment's pointing, you need to place the rebar. That's that's how other software use it. If you study in the US, you will see the moments plotted upward, like frowning at you for. Okay. So I think that's it for this example. Let's move on. I'm gonna go through examples really fast. Okay, new, open, gonna go to examples. So the beam I already showed you. I'm gonna just show it real quick. You can see I added a node here to two elements, making this beam to add the point load there. So it's the same as the other one that we just did. New, open, go to column. It's gonna take a bit more. So we're gonna go to the main. You know how to place the load. So now we're gonna cover this section, preform nonlinear and buckling analysis. It's experimental just because if you're doing something really weird like this really long beam column, it's a beam element. You can see here it's a beam element because columns are beam oriented vertically, right? Okay, so and the problem with this, you see it has 360 inches. It's way too long, like it's 30 feet, and the section is not that great. You see it's like W 18 by 35. It's very slender. It's kind of like a paper. And if you try to to run nonlinear, software is not gonna like it because you need some bracing on this column. It's not realistic. If you run it, you're gonna get this error, stability error. Telling you that the eigenvalues are non-zero. So just tell you to go back and just change the length of this column. You just make it a 10-foot column. So you see 120, now it's reduced. If you rerun the analysis, you're not gonna get that error. It's gonna do non-linear. First, this one. Basically, we're reducing the stiffness by 20%. That's what common, and somewhere in the code that when I was reading it, that's what you need to use. You don't use the full stiffness of your material, you reduce it by 20%. Okay, it's perform non-linear buckling, and then it's give you the mode. Mode 1 give you the critical load factors 8. If you double the load, this number gonna cut by half. I can do that real quick just to demonstrate. If you go to loads, and then instead of 250, I'm gonna do 500 just to make it clear. 500 kips, and then you see it's updated there. If I run the analysis, remember this 8.11, go back, scroll to the top, you can see this number cuts by half. So okay, that doesn't mean the structure is passing, so it has a higher stresses. If I go to material, it's 36 KSI. I'm gonna change it to 50. That should increase the capacity of the column. And you can see this 1.3, it's going to change when I run the analysis. You can see it did change. So and that's it. I covered the column. I'm gonna cover other real quick. I'm gonna do new. I'm gonna go to open and then frame. Same thing. The only thing I want to cover here, you see frame columns and beams are beam elements, and then this one, this tangent member, slender, and they subdivide it to 100. I don't think you should do that, but I just for demonstration purposes. And then you can run analysis if you want, give you the same thing. These ones are problematic. You can change them. You can see reaction display. You can use this one to help you zoom in or zoom out, and then always go home if you don't like that. Reaction see in this case they are you can move them up. Um, Bending moments. I already talked about bending moments. Shear, axial, displacements. You can reduce it here because it looks like way too much. Just put it, cut it in half, and then show displacement. This one again does not affect structure, just for you to visualize things. But this one does. This one is actually you reduce the stiffness of structure. So you can use one if you want the exact value, but this is why I put it as default. Okay, so I covered that. Let's me move on to the next example that we have. We have a multi-story building. Same thing. If you run analysis, I'm not gonna check this one. You can if you want, but the problem with that is it has like what? Subdividing this one to 100 is too much. An unrealistic thing, it just to stress the software. If you run it, this thing gonna freeze for a little bit. Watch. 1, 2, 3, about 3 seconds for it to finish calculation. Because that's horrendous calculations. It's crazy how many matrices and then it's assemble all that. It does them really quick, but anyway, let's me cover the most important, not the most important, but equally important uh, type. We have beam. We're using beams for columns, so they carry moments, shear, and axial. But if we use truss, it's carry only the axial, and that's what I'm gonna talk about. Let's add new, then open. I'm gonna go to truss. You can see truss elements. You can run the analysis. It has 2-point loads, 32 and 8. Let's give you the values. If you go to reaction, you can see reactions. If you go to bending moment, there's nothing. If you go to shear, nothing. Axial, yes. And this element is experienced the most axial. It's kind of counterintuitive, but if you look at it, you'll think, okay, this one maybe gonna have the same if you're just looking at it. But this one actually has the lowest axial load compared to this. And even this one takes more axial than this. Anyway, I don't want to talk in detail about this, but I try to make this video as short as possible. I think this is good time to stop. Thank you for watching. Have a nice day.